welcome everybody. Well, excited to have you here to our Solar Climate Intervention Virtual Symposium. And today we have two very fantastic speakers, Ewa Bednarz and Colleen Golja. And Ewa will start. Ewa is currently a research scientist at the NOAA CSL. And she is also a visiting scientist at Cornell, where she has spent the last 2 years as a postdoc. Ewa has done a lot of work on climate intervention and a lot of various papers. And today she will talk about injection strategies, a driver of atmospheric circulation and ozone response to stratospheric aerosol geoengineering. And before you start, Ewa, a quick announcement. So just for everybody who's joining, and I will say that also afterwards, if any of you would like to present during this symposium, please send Matthew or me an email, and we'll be happy to put you on the list of presenters and contact you. But I'm also motivating people to nominate people or papers that they think would be worth presenting at the symposium. And then we also take that into account. Okay, and with this, I do not want to wait any longer to have Ewa start. And Ewa, you have about 20 minutes, and then we'll do questions for about 10 minutes. Thank you.
Okay, awesome. Thank you very much, Simone, for inviting me, and thank you very much for everyone for being here. So I'm going to talk about the stratospheric aerosol injection, and in particular the SAI strategy. So when and where do we inject sulfate aerosol precursors, and how that determines the resulting climate response to stratospheric aerosol injection. So yeah, it works. Okay, awesome. So the work I'm going to be talking about has been largely written up, and you can refer to it if you're interested. It's currently, there are 2 papers that are being in review on eGeosphere. There is the paper from Yan Zhang, a PhD student at Cornell, introducing a comprehensive set of stratospheric aerosol injection strategies. And there's another paper led by me that looks at a little bit more detail on some of the atmospheric and climate responses and their dependence on SAI strategies. So I'm sure most of you are familiar with what stratospheric aerosol injection is, but just to put everyone on the same page. So SAI relies on the injection of sulfate aerosol precursors into the lower stratosphere, and once formed, can you see my screen? Oh, you can, awesome. So once formed, sulfate aerosols reflect a portion of the incoming solar radiation, thereby reducing surface temperature. And I do want to point out 2 things. First of all, the reduction in the incoming solar radiation from aerosol reflection does not just cancel the greenhouse gas induced warming. This is because there are differences between the short-wave radiating forcing of sulfate and the long-wave radiating forcing from greenhouse gases. And this can then lead you to distinct climate impacts from SAI. And the second thing I want to point out is that sulfate aerosols are not inert. So once in the stratosphere, they absorb a portion of the incoming solar radiation and a portion of the outgoing terrestrial radiation, giving you a warming in the lower stratosphere. And this is important because it can affect circulation both in the stratosphere by changes in the horizontal temperature gradients and also in the troposphere below. And both of those effects can then lead to distinct side effect, climate response to SAI that we also can refer to as a side effect. So previous studies show some of these unintended side effects of geoengineering with stratospheric aerosol injection. So one commonly pointed out side effect is the fact that the heating in the lower stratosphere in the tropics tends to strengthen meridional temperature gradients in the stratosphere, and this gives you a strengthening of stratospheric jets in both hemispheres. This is shown on the plot on the left-hand side. And what happens is that during the dynamic reactive season, so we are talking winter in the northern hemisphere, so winter in the northern hemisphere, DJF, this response can then propagate down to the troposphere, giving you changes in surface climate. And this manifests itself as changes in sea level pressure that are shown in the middle panel. We've got this decrease in sea level pressure over the Arctic, and a pattern of changes, a pattern of increasing sea level pressure in the mid-latitude. And this is commonly referred to as the positive phase of the North Atlantic circulation. And this is important as it drives changes in winter temperature and precipitation patterns in Europe and North America. And another commonly pointed out side effect of SAI is the impact on stratospheric ozone. So the black line shows the evolution of Antarctic springtime ozone column under a control simulation with time varying greenhouse gases and ozone depleting substances. And then we've got this gradual recovery of stratospheric ozone to its pre-1980 levels. And then what happens when we inject sulfate aerosol precursors into the lowest stratosphere, the Antarctic ozone goes down, and then the recovery of Antarctic ozone is delayed by a few years or a few decades, depending on scenario. And this is because sulfate aerosols, they provide active surfaces on which heterogeneous reactions can occur that convert halogens from inert form to more active form that can then lead to catalytic ozone depletion inside the polar vortex. So what is important, what I want to point out here is that these studies, like by far most of the previous SAI studies, use only a single location for SAI, or at least a single set of location of SAI, usually the tropics or the equator. And it is still not well understood how would these side effects differ, if at all, if a different SAI strategy was used instead. So what I want to talk about for the rest of the talk is how does the choice of the SAI strategy, so when and where do we inject sulfate aerosol precursors, how that determines the resulting atmospheric and climate response to SAI. So I'm going to be using simulations carried out with the CSM2 WACAM 6 model. It's a high-top Earth system model with interactive aerosols, stratospheric chemistry, and interactive ocean. And I'm going to be using 4 SAI simulations, each with a different SAI strategy. So I'm going to explain what those strategies are in a second. For now, let's just say that all of those 4 SAI simulations go from 2035 to 2069 with SSP2 simulation, SSP2 scenario being used as a background greenhouse gas scenario. And so the injection rates in those 4 SAI strategies are modified as the simulation occurs, so that all of those SAI strategies achieve the same level, the same annual global mean surface temperature. So this is illustrated on the plot here, which shows the evolution of global mean surface temperature in the control SSP2 simulation in black. And then in the 4 SAI strategies in colors, we see in the SSP2 simulations, the temperatures goes up due to greenhouse gas induced climate change. And then in the SAI simulations, we see a decrease in temperatures as the SAI started in 2035. And then all 4 SAI strategies settle down at the levels corresponding to 1 Kelvin above pre-industrial. There's a little bit of differences in the actual temperatures between those 4 strategies, but for the sake of this talk, you can think of them for now as achieving exactly the same global mean surface temperature. Okay, so now let's talk about what those 4 SAI strategies actually are. So first of all, there's what's been commonly used in the past for the SAI simulations. It is the injection of SO2 at the equator year-round in the lowest stratosphere. Then we've got 2 pairs of symmetric SAI strategies, injecting aerosols at the pair of 50 north, 50 south, or a pair of 30 north, 30 south. And again, we've got an constant injection throughout the year at 22 kilometers. And then we've got what I'm going to be referring as a polar strategies, where sulfate aerosols are injected in the high latitude at 60 degrees north and south. And this is not going to be a constant injection throughout the year. This is going to be injection that occurs only springtime in each hemisphere. So we are talking March, April, May at 60 degrees north, and September, October, November at 60 degrees south. And because the tropopause is generally lower at high latitudes than in the tropics, we can inject the sulfate aerosols lower down at 15 kilometers rather than 22 kilometers. So here this plot shows the simulated mass mixing ratios in the 4 strategies. We see large concentrations of sulfate for the equatorial strategies that are found inside the tropical pipe. And then these concentrations become smaller and more spread out as the injection goes from the equator to the tropics and then to the subtropics. And then we see much smaller sulfate MMRs for the polar injection strategies. And this is because the lifetime, if we inject aerosols in the high latitudes, the lifetime of aerosols becomes much shorter, and so smaller particles are being formed only, so which has comparatively less mass. Okay, so these were the yearly means. So here this plot shows the temporal evolution of aerosol optical depths. So we've got the latitude on the x-axis and the month on the y-axis. So for the annual injections, remember we adjust the injection rates so that the same global mean surface temperature is reached, but in each year, the injection rate is constant from January to December. So what we find for those annual injections is that despite the constant injection rates throughout each year, we still see a structure of the seasonality and a structure in this anomalous aerosol optical depth from sulfate. And this is because stratosphere is not steady, it's a dynamic system. So we still have a seasonality in transport in the stratosphere and the seasonality in the source of OH that is needed for the formation of sulfate. And that gives you some sort of seasonality in the anomalous AOD produced. And then for the polar strategies, remember we only inject SO2 in spring and each hemisphere. And because it takes around 1 month for the SO2 to oxidize to form sulfate, the anomalous AOD is found mainly in summer in each hemisphere. And this is actually very efficient, as most of the sunshine, this is where most of the sunshine actually reaches the high latitudes, mid and high latitudes. And then because the lifetime of aerosols is much shorter in the high latitudes, the AODs then
questions.
That's not the checklist.
Well, it's a bit of checklist, although you haven't really.
Can we please stop? Can we please do the questions afterwards?
Question of...
it's
Oh, okay, thank you.
Sorry, and so what I was saying, so because the lifetime of aerosols in the high latitudes is much shorter, if you inject at high latitudes, the AOD then goes down in autumn as the aerosols are being removed from the stratosphere. Okay, so we've got 4 SAI strategies. For simplicity, I'm going to talk a little bit about all 4 of them, but I'm going to focus mostly for the equatorial strategy and the polar strategy as representing somehow 2 extreme ends of the possible strategy space. Okay, so let's look at some results. So here we've got the simulated changes in temperatures, yearly mean changes in temperatures for the equatorial strategy and the polar strategy. So I'm going to be looking at the last 20 years of each SAI simulation minus the same period in a historical period where the same global mean surface temperature is found, so that the difference is effective in the global mean surface temperature between the SAI simulation and the historical period is 0. So what we find is that the simulation achieved the same global mean surface temperature. We still have a lot of differences in temperatures, both in the troposphere and in the stratosphere. So in the troposphere, we see that for under the equatorial injection, most of the cooling occurs in the tropics and the northern hemisphere mid-latitudes in the troposphere, while the high latitudes are still allowed to heat up because we don't really cancel the greenhouse gas induced warming. And then for the polar strategy, we find that most of the cooling occurs near the surface in the mid and high latitudes, while tropical troposphere is still allowed to warm up. And this gives you changes in horizontal temperature within the troposphere that would then be very important for determining tropospheric circulation. And then in the stratosphere, we see this warming in the tropical low stratosphere as aerosols absorb terrestrial and solar radiation. But we find that this magnitude of this warming is actually differs significantly between the equatorial and the polar strategy. It's much significantly larger for the equatorial strategy and is way more confined to the tropics. And then it's much smaller for the polar strategy. And on the right-hand side, I've got a measure of this lowest stratospheric. On the right-hand side, I've got a measure of this lowest stratospheric warming in the tropics for each of the 4 strategies, and we see a very strong dependence of how strong this lowest stratospheric heating is, depending on the SAI strategies. Okay, and the reason why that matters is, first of all, that changes in lowest stratospheric temperatures, they can affect the concentrations of water vapor that can enter the stratosphere. So the concentrations of water vapor in the stratosphere are generally very low. The stratosphere is very dry, and water vapor tends to enter the stratosphere via what we call the cold point tropical tropopause, where the air is largely dehydrated depending on the temperatures at this cold point tropopause. And so any changes in temperatures around the cold point tropopause will basically change how much water vapor can enter the stratosphere. And so an increase in lower stratospheric temperatures can then increase concentrations of lower stratospheric of water vapor in the stratosphere. And the reason why that matters is that in the stratosphere, especially in the lowest stratosphere, water vapor is a greenhouse gas. It absorbs a portion of the outgoing terrestrial radiation and then re-radiates it back to space. And so this SAI-induced increase in stratospheric water vapor acts to directly offset a portion of this SAI-induced cooling at the surface. So this cooling we are getting from the reduction of incoming solar radiation by sulfate aerosols. And the plot on the right-hand side just shows the simulated changes in water vapor at the tropical tropopause. Again, we see a very strong dependence of the SAI-induced stratospheric moistening on the SAI strategy. Okay, so we can do some back of envelope calculations to estimate the radiating forcing from this SAI-induced stratospheric moistening. So the radiating forcing of water vapor in the stratosphere has been previously estimated to be of around 1/4 of a watts per meter square per 1 ppm increase in stratospheric water vapor. And we can basically plug this number into the changes in water vapor that we simulate in those simulations. And we end up with a radiating forcing of the SAI-induced stratospheric water vapor increase of change varying between 0.5 at the equatorial strategy to around 0.2 in the polar strategy. Those numbers presumably don't mean that much to most of us, but to put that in context, I don't know whether the panel on the Zoom actually, hopefully not, obstruct this view, but we can compare that with the radiating forcing from sulfate, that is direct radiative cooling from a reflection of incoming solar radiation by sulfate. And in that case, we've got the numbers that range from around -3 watts per meter square for the equatorial strategy to around -1.5 for the polar strategy. So if you compare the two sets of numbers, you reach a conclusion that the SAI-induced stratospheric moistening is a small but nonetheless important contribution to the overall radiative budget, and thus it needs to be factored in any considerations of efficiencies of various SAI strategies. Okay, we're there. So another important consequence of the SAI-induced warming in the tropical lowest stratosphere is the strengthening of the meridional temperature gradients in the stratosphere and thus strengthening of the jets in the stratosphere. So we find that we see in the equatorial strategy, we've got significant strengthening of jets in both the southern and northern hemisphere in the stratosphere. This then becomes much smaller for the polar strategy. And on the right-hand side, I've just got a measure of this strengthening of the northern hemisphere and southern hemisphere polar vortex. Again, we see a very strong dependence of the on the SAI strategy. And the reason why this matters is twofold. First of all, these stratospheric responses, westerly responses, can propagate down to the troposphere and affect things like extratropical modes of variability, like northern and southern annular modes, which in turn are very important in determining weather patterns in the mid and high latitude. And the second reason why this matters is that strengthening of stratospheric jets gives you a strengthening of potential vorticity gradients, and this in turn impacts on mixing, introducing mixing efficiency, which would be important for transport of tracers in the stratosphere like ozone or even the concentrations of sulfate from SAI. Okay, so changes in zonal winds are not the only aspect of stratospheric circulation that can change under SAI. Another important aspect is the SAI-induced changes in Brewer-Dobson circulation. So the warming in the tropical lowest stratosphere acts to change the atmospheric static stability, both in the troposphere and in the stratosphere. And this has two consequences on the residual circulation. First of all, it tends to weaken the shallow branch of the Brewer-Dobson circulation, and things like upwelling in the upper troposphere and lower stratosphere. And we see again very strong dependence of this SAI-induced changes in Brewer-Dobson circulation on SAI strategy. And then regarding the deep branch of the Brewer-Dobson circulation, so the proper stratospheric branch of the Brewer-Dobson circulation, we now see a strengthening of the deep branch of BDC with a very strong dependence of the magnitude of the response on the SAI strategy that is being used. And again, the reason why this matters is that it impacts transport of tracers in the stratosphere, including water vapor and stratospheric ozone. I think I'm running out of time. Let me just, so here we've got the simulated changes in ozone in the stratosphere. These are yearly means. And I'm comparing the last 20 years of the SAI simulations minus the same period in the SSP2 simulations. So we don't have to worry about things like long-term changes in greenhouse gases in ozone depleting substances. So we see that for the equatorial strategy, we've got this rather complex pattern of changes in ozone in the tropics and mid-latitude. We've got increases in ozone in the tropical lower stratosphere, decreases in ozone in the mid-stratosphere, and then increases of ozone again in the upper stratosphere and the northern hemisphere, mid and high latitudes. And they are largely dynamically driven. So I talk about SAI-induced changes in Brewer-Dobson circulation. And so we find that if you go to the polar strategy, where the changes, SAI-induced changes in the Brewer-Dobson circulation are now much smaller, we see that the lower stratospheric increase in ozone is now much smaller, and then everywhere else, the responses, ozone response to this largely go away. And for the Antarctic, well, another thing I want to point out is what happens in the Antarctic high latitudes. So we see that, in fact, both the equatorial strategy and the polar strategies, they both see significant decreases in Antarctic ozone in the lower stratosphere. The interesting thing is that this most likely happens via different mechanisms. So for the polar strategy, this decrease in stratospheric ozone in the Antarctic is because of we've got a lot of aerosols in the high latitudes. These convert chlorine to active forms that enhance catalytic ozone depletion inside the polar vortex. For the equatorial strategy, however, not that many aerosols make it to the Antarctic high latitudes. And so this decrease in Antarctic ozone occurs most likely because we got the strengthening of jets in the Antarctic, the polar stratosphere becomes colder, and the catalytic ozone depletion accelerates. And also because we strengthen jets in the Antarctic stratosphere, you decrease mixing of ozone from the ozone poor air inside the polar vortex with the ozone rich air in the tropics. And all of that basically that illustrates the complex interplay of various processes that determine the SAI-induced changes in stratospheric ozone. And let me just very quickly point out the last thing, which is what happens to tropospheric circulation in the high latitude. So here we've got the SAI-induced changes in sea level pressure in the Northern Hemisphere winter, so DJF. And in the equatorial strategy on the left-hand side, we've got this SAI-induced weakening of decrease in sea level pressure over the Arctic and increase in sea level pressure in the mid-latitude. And this corresponds to this positive phase of North Atlantic circulation that I pointed out previously. That is a response that is one of the responses that has been previously frequently pointed out as one of the likely side effects of stratospheric aerosol injection that is not easy to avoid. However, what we have on the right-hand side, I plot this NAO sea level pressure index for the 4 different simulations. And we see that for the equatorial strategy, we see a significant increase in NAO index that is statistically significant. However, for the 50 North and 50 South, the response becomes now much weaker and not statistically significant. And then if you go to the 30 North and 30 South and the polar strategies, the positive phase of NAO under SAI basically goes away. And that basically highlights that some of the side effects of SAI might be potentially reduced upon a design of an optimal SAI strategy. Okay, so let me just summarize. I talk about stratospheric aerosol injection and how that can alter stratospheric and tropospheric temperatures with implications for the stratospheric water vapor, ozone, large-scale atmospheric circulation, and then eventually what we all care about being the surface temperature and precipitation patterns. But if you remember nothing else from my talk, do please remember that the response is strongly dependent on the location and season of SAI, so what we call the SAI strategy. And really more research is needed to understand the atmospheric and climate response to SAI, the complex interplay of various processes that actually determine it. And then also its dependence on SAI and strategy, and therefore laying ground for future efforts into optimization or finding a optimal strategy that minimizes the SAI side effects. And again, just want to point out that if there's anything that I said that is interesting, please refer to one of the papers, any of the papers that we've written up on that subject, or you can just get in touch with me or any of my co-authors. And with that, I want to thank you for your attention and ask if you have any questions.
Thank you. Very good. Yeah, thanks, Ewa. Great talk. And
I'm sorry I overran slightly.
no, that's fine. We'll do a few questions. We started a little late. So please, if you have questions to this talk, raise your hand. Yes, there is one question already. And you can also place your questions in the chat. So yeah, Hong Wai, please go ahead and ask your first question.
Okay, thank you, Ewa, for this great question. Sorry, for this great talk. So my question actually is about a technical question. So I'm also working on something to separate rhodopsin circulations, deep and shallow branch. So for me, I use like 50 hectopascal to separate. I'm just curious, how did you separate the shallow and the deep branch of rhodopsin circulation in your research?
I mean, yes, no, I had the same problem. There's I think different people define the different branches of the circulation very, very differently. There's like the earlier study from Fu and Lin from like 2013. They basically define not just the deep and shallow branch, but they also define the transition branch. So for here, I define the shallow branch as 170 hectopascal, and then deep branch as everything above. But it does, yeah, I do understand there's lots of different definitions in literature, and I think lots of people define the different branches in different ways. And that's a very good point that you're making.
Thank you.
Thank you, sir. Are there more questions for Ewa? If not, I can ask a question. Please also raise your hand while I'm asking. So I find the ozone response very interesting compared to the polar and the equator and the other places. And you pointed out the Antarctic response, but I'm also interested in the Arctic. And I saw that you showed, I think, annual mean ozone response, but I'm really interested in springtime ozone response for the Arctic in both. Have you looked at that? And how would that look like?
I did look at that. There is, I think for the equatorial strategy and the 50+50 strategy, there isn't, at least for like, obviously there's variability, but there is, in terms of like enhanced heterogeneous ozone depletion, enhanced heterogeneous activation of chlorine, there doesn't seem to be that much impact. I haven't looked daily, but there doesn't seem to be that much impact on under the equator and 50 north. For the, I think the biggest impacts I could see are actually for the 30 north and 30 south, because then the aerosols are, we do see a little bit of ozone depletion in the Antarctic because the aerosols actually can reach the high latitudes. For the polar strategy, we see some depletion, but from what the most statistically significant response occurs actually in the summer, which to some extent makes sense because that's when the aerosols are, but it's not exactly inside the polar vortex. So yes, I have started looking at it, but it's even more complex.
Yeah, that seems very interesting because re-injecting in the polar regions, we're always concerned about the ozone.
Yeah.
Great. Any other questions, comments? And while maybe somebody's thinking about this, we can have already Colleen start sharing her screen or can stay on time. That would be great. That looks good. This is not on slideshow yet. So if you still have a question for Ewa, or you can certainly reach out to her, and then you can still put your questions in the chat, else we'll start moving forward now. This is great, it's 9:30, halfway through. So our second speaker is Colleen Golja, and she had obtained her PhD in Harvard University in 2022. and now is working on mostly on aerosol microphysics related to stratospheric aerosol injection. She has spent the last year working as a postdoc with Mariana Lintz and on stratospheric dynamics, and is then also going forward to work on UTLS processes at the Empirical College in London this fall. So with that, Colleen is talking about stratospheric heating, investigations into the indirect effects of stratospheric aerosol injection. Colleen, please go ahead.
Okay, thank you. This was, I think, very well timed. I think Ewa has given us a really great introduction to why you should care about stratospheric heating. And obviously, Ewa was focusing on how different injection methods might minimize the impacts of stratospheric heating on kind of the response to SAI. And I think at the very last slide, she had listed that one of the things that wasn't investigated was the kind of intermodal differences between the response to SAI and specifically to stratospheric heating. And so that's kind of where this work plugs very well in. So I think this hopefully is very well motivated. So thanks, Ewa. Let's see, will this work? There we go. Okay, so I have just a brief introduction that I will kind of go through because I presume everyone has a little bit of background, but stratospheric aerosol injection, again, the idea that you could put this kind of layer of reflective particles, mostly people think about sulfate aerosols, into the stratosphere to reflect some incoming solar radiation back to space, which would potentially offset some of the risks from increasing concentrations of greenhouse gases in our atmosphere. So there's a bunch of different feedbacks that we want to think about when we're thinking about what this could potentially do. Aerosol cloud feedbacks are something that we think about. You heard Ewa talk about kind of the stratospheric ozone response to increasing the burden of sulfate aerosols, so kind of stratospheric chemistry feedbacks. You have surface land impacts in how plants are now receiving light in the form of diffuse first direct light. And then you have this absorption of the aerosol particles themselves, which can lead to a localized stratospheric heating. So when we talk about stratospheric heating, that's kind of where that's coming from. And as Ewa pointed out, that is really a function of the concentration of aerosol you're injecting and the injection strategy you use. So hopefully you're convinced that the injection strategy can really serve to minimize that particular feedback. Now, in a lot of the previous literature, and I guess less so now as I think the field is growing, a lot of the models that we were using were these using an idealized top of atmosphere reduction in the solar constant as kind of this like first order way to model solar aerosol or stratospheric aerosol injection to kind of see what the basic like first order impacts would be. And they literally just kind of turned down the solar constant, or they turned it down as a function of season or latitude. But by doing this kind of really simple representation, you do miss quite a lot. And I'm going to quote Visione et al. From 2021, Daniele, I think you're on this call, that dimming the sun does not produce the same surface climate effects as simulating aerosols in the stratosphere, which is hopefully pretty intuitive because you miss a lot of these aerosol feedbacks in doing so. And again, one of these main things we miss is that aerosols are producing a localized stratospheric warming that invokes various changes at the surface and in the upper atmosphere. The other things that are happening that I will kind of list but ignore is that, again, we don't produce the same temporally and spatially uniform reduction in shortwave radiation if we have aerosols injected, because, you know, again, injection strategy would be different versus transport by circulation, et cetera. You don't capture kind of the surface land impacts, and then you don't necessarily capture any of these kind of complex feedbacks with stratospheric chemistry, which has implications for both the stratospheric and tropospheric ozone and radiative balance, which kind of feedback on everything. So focusing just on this, I want to point out that the system is incredibly complicated, and Daniele had a plot or a figure that I love that's kind of trying to identify how complicated SAI is, and I've kind of recreated that with just a focus on just stratospheric heating. So removing the aerosols and just saying, well, if I just impose a magic stratospheric heating, alone heating itself can still have really complicated feedbacks. And it's as you perturb this kind of temperature profile in the stratosphere, you have a number of surface effects through kind of radiative feedbacks, chemical feedback on radiative feedbacks, and you have these interesting kind of very confusing loops. So when I'm looking at stratospheric heating, I'm actually holding stratospheric ozone constant so that it can be removed from this complicated diagram. And then I'm really interested personally in focusing on how kind of modification to the vertical temperature profile, yes, that is your figure, Daniele, vertical temperature profile can modify the circulation, impact kind of greenhouse gases in the stratosphere. And we're thinking both about, in this case, if we remove ozone, I'm really thinking about stratospheric water vapor, which hopefully you're now convinced from Ewa that that is an important constituent of the stratosphere, which then feeds back on vertical temperature profile and can feed back on circulation. You have this interesting cycle. Previous literature, and also what Ewa has just presented, has looked at kind of how stratospheric heating itself is an important component to capture the surface impacts of SAI. So there were studies done, and I'm going to let this out, with kind of these large forcings. So also what Ewa showed was a relatively large stratospheric heating signal from a relatively large forcing. I think, Ewa, you can correct me if I'm wrong. And then these previous papers by Bednarz et al. In 2020, Jones et al. In 2021, we're looking at relatively large temperature tendencies of approximately 1.2 Kelvin per day forcing, and found this figure to the right is from Jones et al. On the left is UKESM, on the right is CESM, and you kind of see, Ewa showed this too, the surface signal of the kind of NAO, so the North Atlantic Oscillation. You see this kind of persistent projection into the positive phase of the NAO, which is important to people who are experiencing weather on the surface. So I think kind of grounding ourselves in what real life things we as people experience. The NAO has impacts for precipitation, especially over the UK and Northern Europe. So we care about these, like if we're going to think about doing this, you know, we want to make sure we're prepared for the outcomes. When there are these kind of smaller forcings, which are more similar to what like a volcanic eruption, relatively small, this kind of goes back and forth in the literature. It's not to say that stratospheric heating isn't important, but it might not be as substantial because it's falling within natural climate variability. So there's kind of, I think, this interesting question of how do we quantify the uncertainty space within our models to understand what the kind of range of impact of stratospheric heating could be. So there was a model intercomparison done quite a few years ago now to try and isolate the impact of imposed stratospheric heating within a set of diverse climate models. So I've listed here the 5 models we've used and the collaborators who ran these ensemble members. And what we basically, well, what they did was to impose a temperature tendency. It has a seasonality to it, but it is zonally symmetric, zonally symmetric. And this was extracted from a run that was done with aerosols that were allowed to evolve. But basically using radiative transfer code, we extracted that heating from that aerosol load. So that was equivalent to about a 2 watt per meter square reduction in radiative forcing that was then doubled. So this is approximately equivalent to a 4 watt per meter square forcing. So this is the experiment that we did. And I think what's really important to talk about is the major model differences. When we're thinking about inter-model comparisons, we really want to understand why we think the models are going to be potentially quite different in the first place. One thing we really know about the stratosphere is that as you increase the vertical resolution of a model, we know that we can very much capture the stratosphere much better. So I think it's important to note here when you look at the different levels that each of these models is using, we go from about 30 levels to up to 80 vertical levels. And so that would make me think that, hey, maybe my rock with all these extra levels is going to give me a better result, but that is just kind of the first order thought. Additionally, we kind of are interested in models that are representing the QBO. So I think one important thing to note is that we have this natural oscillation in the winds in the tropical stratosphere. Some models have a nudged QBO. Some models are able to reproduce this kind of internal QBO that I don't think anyone's doing a super great job in the cases here, but it is important to note that it's a feature that's different between the models. So what we see when we impose this heating, we get a stratospheric temperature perturbation. So hopefully that is very intuitive. And what we see is really similar to what kind of Ewa has shown. I'm showing you the annual mean response, but you see, and it's much weaker than what Ewa showed, but we see that we get this modification to the stratospheric temperature profile. And I think they all look relatively similar, but I hope what you can take away is that some of these models, I would say, especially MyROC, the temperature profile that results from the same imposed heating is pretty different. Additionally, you see, and I guess the colors are actually a little hard to see on my screen here. But we also see that the peak temperature change, for example, in CESM at just above what would have previously been essentially the cold point in the tropical stratosphere here, is quite a bit bigger than other models by about 1 Kelvin. So I think I'm interested in understanding why these are so different. The changes to the meridional gradient in the stratospheric temperature impacts the zonal mean wind. And again, like Ewa showed, we kind of see this strengthening of the stratospheric jets. And consistent with what she had said, we also kind of can see this weekly bleeding into this troposphere. This is again the annual mean, but during these kind of coupled seasons, we would expect to see the relationship between the stratospheric change and the troposphere a little bit stronger. So hopefully you can kind of tell that there's a little bit of green, meaning we're kind of weakening at the edges of this kind of mid-latitude in the troposphere and expanding what seems to be the Hadley cell, which is really consistent with previous work. Now, again, the question that I'm interested in is why are these not all doing maybe, if they were all the same resolution and all the same microphysics and we knew the physics was all correct, then these would all be the same. But the reality is these are all slightly different, and what's really driving the difference is what we're interested in. And then I know Ewa focused on DJF. I would also say I'm interested in the kind of the Northern Hemisphere DJF response, just because we know that this impacts this kind of positive phase of the NAO signal that was cited in the previous papers and by Ewa as being something that we know is a persistent signal from the stratospheric heating. And I really want to understand, how different is that in different models. So what's the uncertainty space around that surface response? And that must be coming from the stratospheric response. So for example, in MyROC, I think what you see is you have this pretty large visual temperature change, but in reality, that's not serving to modify the vertical temperature gradient. So you don't get the same strengthening in as far as like the analytical thermal wind adjustment in the Northern Hemisphere stratospheric jet. So you would expect not to have quite as strong a signal at the surface. So this is kind of those baseline stratospheric responses. This is just another way to kind of view, I think, the polar vortex from above. This is now if you're looking straight down on the North Pole. And again, you kind of see CSM and GFDL and UKASM have these kind of really similar responses. And the question really is, why is GISS and MyROC not necessarily having or exhibiting the same response? So what are the key differences and where are they coming from? So that's kind of what I've been glacially working on. If you know me, you've probably seen me give some variation of this talk like several times over the past years, and I'm trying to wrap it up. So what are the key differences and why do we care? So one of the things I was really interested in looking at was, obviously we know that stratospheric heating, again, Ewa, perfect introduction, provides a mechanism through which you are warming up this area where water is traditionally being dehydrated as it's entering the stratosphere. So what we expect to see is stratospheric warming leads to an increase in the influx of water vapor into the stratosphere. So first, if I just look at the baseline control for each of the models, I really want to understand, the models are all different. How different are they? I'm showing here a measure of, let's qualitatively look at this together right now, a measure of the stratospheric water vapor. GFDL and UKESM seem to have slightly increased water vapor in general in their baseline climatology. If I look just higher up in the stratosphere and I kind of ignore what this kind of tropical tropopause region is, this is kind of the amount of water that's reaching up as we rise through a column of air through the tropics, right? If we look above that point, so what exactly is the concentration of water vapor reaching the actual kind of upper stratosphere? We see pretty different results. I think GFDL and GISS tend to be a little bit more saturated, UKESM and CESM less so. And I have to investigate this further. I think UKSM has a relatively like flat line, but we expect to see this dehydration as we go from equator to pole. And so this behavior is just to say that these models are doing different things to start with, so that when I look at the change from control in the entry of water vapor, it makes sense to me now that maybe these are having different mechanisms through which water is being allowed into the stratosphere. So the change in water vapor from control is a function both of the control kind of mean climatology and the model's response to the stratospheric heating. And the question really is, how do you parse and allocate the roles of both? So the interesting thing here, I think, to see is that GFDL and GISS GFDL is letting in quite a bit more water. And I think you can kind of also see this kind of tracing and transport as you bring water from the equator to the pole. So as we're looking kind of, we had our heating centered at around 60 hectopascals. So you can kind of orient yourself there and then say, you know, GISS seems to be having this kind of very mirrored, very symmetrical response, whereas CSM has something that I would assume is a little bit more intuitive, and that you get this dehydration as you go from equator to pole. But so when I look at this, I was thinking, okay, so what I really want to understand is how stratospheric water vapor transport is happening in each of these models. Like, is it purely based on the cold point temperature, which is now a function of the temperature change induced from my heating? Or is there some other complex dehydration process that these models have employed? And I guess how is my delta in, you know, stratospheric heating playing with those parameterizations? Okay, so this is just to say there's compositional changes that we care about. I think the other important thing to note again is that ozone was held fixed in this study, so you don't have the radiative feedbacks from ozone. We would have radiative feedbacks from water vapor, and you would expect that if you have about a change of 1 ppm per volume of water vapor, that would be about a change of 0.25 watt per meter squared. So here we see, well, I guess I'm going to do some conversion for you in my own head, but you see something relatively small, so less than 1 ppm, but it's still something that we want to understand because each of the models should respond to that in a meaningful way. So the other thing we really want to understand in this context, and I have about 5 minutes left, is changes to the overturning circulation. So one thing to note is that, so Ewa showed us W bar star, which requires kind of more higher frequency output or specific U prime V prime output from the models. So in the intercomparison I don't have the same output from each of the models, and I was not able to do a traditional W bar star calculation to understand the strength of the overturning circulation. So to kind of deal with this, I'm using something called the diabatic circulation, which is, I'm going to show on this right-hand side plot from Lintz et al. 2019. The diabatic circulation is a way to kind of track the value of W bar star. And this plot is showing kind of the ability of M here, which is the diabatic circulation, to capture the patterns of W bar star as a function of potential temperature, which is kind of a vertical coordinate system in the atmosphere. So there's, you know, precedent to using this method, and basically what it does is it takes the diabatic heating rates, which are a 3-dimensional output variable at a monthly scale, and you can estimate the kind of upwelling and downwelling through a potential temperature surface. So when I've been looking at around 460 and about 760 as a measure of kind of the lower and the upper stratosphere. How's the circulation changing through those kind of surfaces? And what's important to note is that the potential temperature as a function of pressure is set by the kind of baseline temperature structure of a model. So you can kind of get a sense of how the mean state of a model is playing into the response here. So far I've done 2 models. Obviously, everyone can understand that with the deadline, I was really hoping to add a couple more in here, and I didn't make my own deadline. But we see that notably, this is showing CESM. We have the pre-industrial control in the solid blue. We have the heating runs in the dashed blue. We have the GFDL pre-industrial in solid red, and GFDL heating run in dashed red. And what we see, firstly, I think if you just compare the 2 pre-industrial values, we see that CSM has a weaker overturning circulation than GFDL in this situation, and it also has a pretty different seasonal signal. I think that's kind of pivotal to note. We also know that like the change that we impose over a model is going to be driven by the mean state kind of bias, or the mean state temperature profile of the model. And this is a perfect example. The mean state of CSM is significantly lower, so that when you impose a heating, you actually raise the overturning circulation almost to be, in some seasons or in some months, equivalent to what a GFDL quantity would be. But we see a pretty consistent increase in the strength of the overturning circulation at 460 in CSM, versus in GFDL, we have this kind of very time dependent or monthly, seasonally dependent strengthening, which I have not totally explained to myself. So if anyone has some really great ideas on exactly why we have this kind of strong seasonal pattern, since this heating rate that we have imposed is relatively similar through the entire year, I would love to hear. When we look a little higher up, I think what's interesting to note here is that GFDL, you no longer necessarily see the heating run or the heating having an impact on the baseline overturning circulation. But in CSM, you actually see that at this high level in the stratosphere, you still have the heating playing a role in changing the overturning circulation and increasing the strengthening of the overturning circulation at this high level, which to me means what I'd like to do next is look through the entire vertical column, as far as if you're looking on a potential temperature coordinate system, to understand kind of how the circulation is either like expanding. In CSM, it looks like we have a higher kind of top to where the heating is having influence over the circulation. And another reason that could be happening is just looking, we look at the heating rates, like the diabatic heating rates from each of the models. And it's important to note that the heating rates from both models, this is the PI control run, they're pretty different, especially if you look through one given pressure level, like approximately that'll give you kind of, if you look at like 70 hectopascals here, and it's about equivalent to the 460 potential temperature, and you see you have a pretty different slice through which you're working, and that can explain some portion of the differences in the overturning circulation. Also, it looks like I'm out of time. I've done a little bit with surface response. It's not as interesting, so we will leave it there, and I will open for questions.
Thank you very much. Great talk. And yeah, this is very interesting, especially as a follow-up from Ewa. I wonder if people have questions. Please leave your slides up. Maybe we do want to look at the surface response. At least I was interested to actually ask that question, but I'll first want to open it up. If nobody right now, I don't see anybody is currently raising their hand. So I would be really interested to see the surface response, because I remember Ayla had discussed that the heating in the stratosphere does, for instance, impact the Asian monsoon and would reduce potentially rainfall. And I'd be really curious to see what other models are showing.
Yes. So what I'm showing here, I have kind of the annual mean temperature response. I will say the hatching here, I've redone the statistics about like 7 times at this point. I tried doing a bootstrap with the PI control and then correcting for the false discovery rate. And we actually see that we can capture different kind of measures of statistical significance. I think what's most important here is the magnitude of change. Sorry, my chat is popping right up. So
yeah, maybe can you put it in slideshow again? It's in.
Oh, yeah. Oh, wait, can you hold on? Are you seeing my presenter mode?
Yeah, the mode that
So
we see the next slide.
we
But
can try swap displays. So there is
up on the top left is a feature swap.
Oh,
Here we go.
thank you. Sorry, I have never known that was a feature. Okay, so I think what we kind of see from, the different models is actually that the surface response is pretty variable between the models. CESM was kind of, I think has been looked at quite a bit, and we see this kind of response that you have this heating over Eurasia, which is dominated by the DJF seasonal kind of signal. UK ESM is cooling down, and I think I gave an AMS talk when I just plotted these, and I have been looking at this quite a bit more. And what I can allocate this to so far is that there's a difference in how the ocean is interacting with the stratospheric heating, and you're able to have quite a bit more heat uptake by the ocean, as far as I can tell so far. So this is something I've been investigating because I thought this was just wrong for a long time, which is never a fun feeling, because you expect when you're putting energy into a system, you should have that energy going somewhere and it should be warming up. And we see this kind of overall global cooling. Yes, we have this kind of relative warming up, but we don't necessarily see the same Eurasian warming coming through in the annual signal. And then MIRAC, we have a relatively low signal. You have these kind of high latitude northern hemisphere warming, and then GFDL, you kind of have this consistent northern hemisphere high latitude warming along with just general land surface warming. The EOF here I'm not going to explain. I don't necessarily want to get into that, but the basic surface response for temperature. If we look at the season, specifically what Ewa has told us, and hopefully everyone remembers that the NAO signal is kind of indicative of this kind of patch of warming over Eurasia and this patch of cooling over the kind of off the coast in the high Atlantic, and I cannot remember the word for that region. You see that signal looking relatively consistent between UKSM, CESM, maybe a little bit in MIRAC, but you're missing some components, and then GFDL doesn't necessarily have this. And one way to parse this apart, and I'm working with Ewa to do so, is to plot this in mean sea level pressure and come up with an NAO index to really quantify the differences in the model response. And I think some of these models will have very little response and some will have more. And the question is really going to be why. I think you can maybe explain this through the stratosphere-troposphere coupling mechanisms in the different models. My understanding is that in order to achieve the kind of surface response as a function of stratospheric response, you need to have this way for the signal to propagate down to the surface. So I think at that point, it's really a question of how the models are parameterizing different features. There we go. Oh no, I have precipitation in here somewhere. Hold on.
Yeah, and if anybody has a follow-up question, please raise your hand already. Then we'll go through this and you can explain the precipitation and I will open it up more again for questions.
I see no questions, so I'll go ahead and just look at the precipitation response. I think the precipitation response in this case, this is with the statistical significance in stippling, which you can see there's no statistically significant change in precipitation in these models, but I think that's because our signal was so low compared to the stratospheric natural variability that we really don't necessarily have enough of a change in precipitation to be able to detect anything in our models. I think it would be really cool to redo this study with a higher signal, but that is selfish and would take a lot of time. So at this time, these are pretty relatively not telling us a ton. Additionally, if you look at the differences in the models, so GISS and UKESM have this signal and kind of over kind of just above Australia, and you see this modification and they're in opposing directions. So that doesn't necessarily help us either. But it is important, I think, to say that the models are definitely not doing the same thing, but they're also not doing anything significant. So understanding the risks, I think, would take a little bit more work in modeling. So hopefully this is interesting. But yeah, I think that's kind of where I'll leave it unless anyone has any more questions. Oh, I see a couple.
Okay, yeah, so maybe you can stop sharing. I do not see hands up. People had to leave and we are really close to the hour. So I think there's a lot of questions and both of you outlined this really well. I have a lot of more questions, but for now, thank you very much for your contributions today. This is recorded. And again, if any of you is interested to give a presentation or want to nominate anybody to give a presentation, we do have a list already lined up, so we'll follow up. We'll have our next symposium on the 19th of May, and we'll announce the speakers in the next couple of weeks or so. Thank you very much. And yeah, it was a great day. Great symposium.